Okay, welcome to this week's CDAC sponsored webinar. I'm especially pleased to introduce today's speaker, Ron Cohen from the Carnegie Institution, a person who's familiar, I think, to many of you and who is a close colleague of mine going back many years. Ron is well known for his many theoretical advances in different areas of materials-based sciences, and therefore is recognized in a wide range of communities and fields for which he's won a number of awards. In geoscience for his simulations of oxides, silicates, and core forming materials. In superconductivity for his early work on the band structure of cuprate high TC superconductors. And in condensed matter physics, more fundamentally for his refinement of exchange correlation functionals in DFT. And then finally in ferroelectrics for his pioneering work on first principles methods to understand the origin of ferroelectricity and oxide perovskite, and also the prediction of colossal enhancements of dielectric properties of these materials under pressure. And all of this work was launched with his classic single author Nature paper in 1992, which last time I checked had some 2,800 citations. So it's also surprising that all of Ron's degrees are in fact in geology, having a bachelor's from Indiana University in 1979 and a PhD from Harvard in 1985. In fact, we met in that time frame when he moved into the dorm room next to mine at the start of graduate school. So that dates us, what, 42 years ago? So Ron was a postdoc and then a staff member at Naval Research Lab before moving to Carnegie in 1990. So Ron, we're looking forward to this update on ferroelectricity and lead titanate. And I see you've included us as co-authors, so this will be very interesting.
Okay, yes, I'm very glad to talk about this. I thought that it should be no problem putting together a talk on something I've been working on for 30 years, but we've been working real hard on this the last few months to try to wrap all of this up, and it's only in the last day or two, last hour that I think I figured it all out, but maybe I'll change my mind during the talk. Anyway, I'm at the Carnegie Institution, and Russ and I were there together for a long time, and this work was started back then. And Mukhtar Ahart, who many of you know, is involved heavily in this work in the experimental side, and as I will show you. So the question is, what's going on in lead titanate under pressure? There we go. Okay, well, first let me say just a few introductory words about ferroelectrics for those of you who are not familiar with them. These are extremely useful materials, and instead of kind of settling down for their middle and old age, they continue to be new, exciting new developments in this field, which are hard to keep up with, and are really, really interesting and exciting. I mean, it's really a new world out there. First, in terms of kind of conventional applications of ferroelectrics, you have everything from sonar and ultrasound. We know you can do very high resolution ultrasound and sonar with transducer materials based on ferroelectrics, and that's been kind of the bread and butter of the ferroelectrics field for many decades. But now they're also very interesting, even in the last decade, as new energy materials. You can get backpacks or shoes that generate power as you walk, or make our little pinwheel devices that generate enough power from wind and cost like $1, you know, and can generate enough power to run a light or something like that in your parking lot. But nowadays, some really exciting things are happening. For example, everyone probably knows how hot machine learning is right now. And all of the machine learning that's being done right now is really simulated in the sense that one has a software program that uses something like a neural network based on operational functional elements that operate, give some output based on their input, and one can do everything from develop self-driving cars with these to have a speaker that listens to your voice and misinterprets what you say. And now there are the ideas of making actual artificial brains out of functional elements instead of just software that runs in a digital computer. And many of these are based on ferroelectrics. And so, for example, this recent paper from a few years ago, making artificial neurons that operate from a bismuth ferrite ferroelectric element. And one can put together, in principle, billions of these interconnected. And people are working on understanding exactly how they work using both theory and experiment. And there's a lot of really advanced work going on in that area. Another area, which of course is of tremendous interest, is in electronics. And ferroelectrics have now been found, such as hafnia, which are compatible with silicon electronics. And people are now building three-dimensional non-volatile memories that will have 10 to 100 to 1,000 times the speed of conventional computer memory, and 10 times smaller, and possible to build three-dimensional networks of these rather than just two-dimensional. So that's really going to change the world also. But going back now 30 years, the question was, how do ferroelectrics work at all? And we thought we had it figured out. One has a double well. The energy goes down if the atoms are displaced off of their centers. And how does this happen? It's just a delicate breaking of the balance of forces. You have ionic forces, Ewald forces that push atoms off center, and you have short-range forces that keep them centered. And it's the balance of these things that's very important. And as you change pressure, this balance changes, so that at least what was thought back then was that you went up in pressure, the ferroelectricity went away, these wells got shallower as you decreased to the lattice parameter. So it seems like a long time to work on something, 30 years, but actually going back farther than that to 1950, Slater said this is a simple enough system that we can hope to fully understand it. So we're still working on that quite a few decades later. So what was thought back in the 1980s was that if you put pressure on a ferroelectric, such as barium titanate or lead titanate, then the ferroelectricity went away. And in fact, experiments seem to show this, so that if you looked at the Raman frequencies this is, I think it's lead titanate. As you go up in pressure in lead titanate, the soft modes go down to 0, and above that was thought to be cubic. And that was great because it was akin to what everybody thought would happen, and it was easy to understand and explain, because the atoms off center in the zero pressure structure, and as you put pressure on, it makes less room for the titanium atom, and so eventually it gets pushed back onto the center again. And so that's the way people thought everything should work. I don't know why that says Japan at the bottom. Okay, anyway. People use theory starting, well, all these years, people have done a tremendous amount of theory on understanding how these materials work. And so look, if you look at any of these perovskites, such as lead titanate, and calculate, these are calculated phonon dispersion curves in the cubic structure. So some of the modes are imaginary. The omega squared is negative, which shows that there's a double well. There's no restoring force for these modes. And so this gamma point or zone center mode is the ferroelectric mode here. And then there's also instabilities at the zone boundaries. And these instabilities at the zone boundaries are related to rotations of the octahedra. And in some materials like lead zirconate, the rotations are more unstable than the zone center mode. So they tend to form what some people call anoferrodistortive structures, where you have a rotation of the octahedron. And then in lead titanate, you have more likely a ferroelectric, and similarly in barium titanate. And people have pointed out some very important general analysis of all this, such as these papers by Nicole Benedict, with an interesting title from a few years ago, Why Are There So Few Perovskite Ferroelectrics? Actually, most of us would think there's actually a lot of them, but if you look at all of the different perovskites that you can make, most of them are not ferroelectric. And most of those have rotations of the octahedra, such as making like the PBMN or the PBMA structure, which have rotations of the octahedra that tend to inhibit the ferroelectricity. And so you can write like a free energy expansion, and very often there's a coupling term between the rotations and the ferroelectric mode, where the coupling is such that they inhibit each other, so that if you have a rotation, it tends to make the ferroelectricity go away. So generally, octahedral rotations were thought to quench ferroelectricity, and the rotations tend to increase with pressure. And so this was another reason that people thought that there shouldn't be ferroelectricity at high pressure, because if anything, things should distort in a different way, and instead of having ferroelectricity. I should also say that Slater's picture of ferroelectricity going back to 1950 was called the Rattling Ion Model, and you can see why pressure would be bad for that, because why would an ion rattle if it was high pressure? So high pressure should squeeze everything together, and there shouldn't be any room for any rattling. We did some theoretical work first, and then some experimental work on lead titanate under pressure, and we found something very surprising. In the process of becoming cubic, it seemed, there was a set of phase transitions where it became monoclinic instead of tetragonal, and in that region, phase transition region, we predicted some extremely high piezoelectric coefficients, in fact, higher than have been observed for any known material. And this was followed up by experimental work by Mukhtar et al. At the Geophysical Lab, and where these predictions were borne out, and they found these monoclinic phases, and exactly like had been predicted. And it's very interesting, because what's known as the morphotrophic phase boundary is this boundary between like tetragonal and rhombohedral phases that form in PZT, or lead zirconium titanate, where one has the most used piezoelectric material form in that composition, in that region. And it also gave some understanding of why those materials are such good piezoelectrics, and what actually happens in that boundary region between tetragonal and rhombohedral. And about the same time, there was this paper, or even a few, about the same time in theory, this theoretical paper by Kornev et al. That I'll talk about later looked at ferroelectricity under pressure in Frizrev letters, where they actually predicted that there would be ultra high pressure piezoelectricity and ferroelectricity. And that's actually the origin of all of this work I'm going to talk about today. So their work really stimulated all of this, and it led to quite a can of worms. So first, the work that we did with Zhigang Wu, where we found this transition from tetragonal to rhombohedral with monoclinic in the middle as one went up in pressure. So that was predicted to happen at about 10 GPa in this region where the earlier experiments had just shown a simple softening of the Raman mode. And I should say that these calculations are done at 0 temperature. And so that, it turns out, is the difference between the earlier experiments, which were room temperature, and then the calculations, which were at 0 temperature. And this led to a better understanding of the whole nature of high coupling ferroelectricity, which I'm really not going to dwell on today. But this idea of polarization rotation, that what's happening in these transition regions is the polarization is rotating from the 001 direction, like a cube axis, towards the 111 direction, which is a cube diagonal. And in the middle, it's monoclinic. And during this rotation of the polarization is when one gets the very high piezoelectric coupling, and that's what we understand now is the origin of very high coupling piezoelectricity, and for example, the single crystal piezoelectrics like PMN-PT and PZN-PT, and further third and fourth generation with other elements doped in as well, that give very easy to rotate polarization direction and then very high piezoelectric coefficients. So all of this was very important from that point of view. And I mentioned this already, this experimental work by Mukhtar, where there are X-ray data shown here that showed this monoclinic phase transition. And there was also Raman showing the transition as well. And then this is the results in the paper by Kornev et al. This is actually their PRL shown here. And then later their long paper in phase transitions. And what they found first in the PRL and later in the phase transitions paper is a little different than what I'll show you today. But basically what they found is that as you went up in pressure, initially it seemed like things were going to become less ferroelectric, but then as you went up in pressure farther, it became ferroelectric again. So they predicted this very high pressure ferroelectricity in lead titanate, really at all pressures. And I'm going to come back to this later, but this really inspired Mukhtar and I and the group to look at and see if we could see this experimentally. And also we tried to do more theoretical work to try to understand what's going on here. So this was published a long time ago, right? So this was published in 2005. So over 15 years later, we're still working on this. So it's not for lack of interesting things to work on. Even in their paper, it says, unlike what was commonly accepted for more than 30 years, and now we're still working on another 15 years anyway. So that's the way science is sometimes, I guess. So one of the works along this route was this paper that Ganesh and I did together trying to map this out. And what we found was quite different than what Kornev et al. Found, what Kornev and Belesh found. We seem to find that it became centrosymmetric at high pressures instead of ferroelectric. And so that seemed to be contradictory with the Kornev paper. But I should say, though, that the energy differences are exceedingly small. And so that's really where a lot of all of this problem comes in, is that it really starts to be a matter of calculational accuracy, of understanding exactly what's happening in these systems. And that's, it's a lot easier to study systems where you have big changes, but when you have small, subtle changes, it's hard. And on the other hand, the reason that ferroelectrics are useful is that they're very sensitive materials, and that means that they have very small energy differences between one state and another. And so the fact that they're interesting and useful is the same reason why they're hard to study. So Mukhtar and I decided to do second harmonic generation experiments. Mukhtar is the one that actually did these, along, I think, with Alex Goncharov. And the idea is you put in a laser at some given frequency, and you look for a response at 2 omega, at double the frequency. And so typically you use like an infrared laser, and then look for 2 omega in the visible. It's interesting, I was just refreshing my memory about second harmonic generation and reading a Wikipedia article today, and I had not remembered this, that when the original paper was published on second harmonic generation observed in quartz, which was shortly after the discovery of the laser and development of the infrared laser, there was a spot on the photograph that showed that they had the second harmonic being generated. So the publisher thought that they just had a spot on their photograph. So he photoshopped, in the equivalent of those days, photoshopped it out. So their actual paper doesn't even show the second harmonic signal because it was edited out in the paper. I thought that was rather amusing. So, but the bottom line is it's hard to do these, especially this was done in the diamond Endel cell under pressure, and so one has to observe the signal. The reason for doing this is that in a centrosymmetric material, you don't get any second harmonic effect, and so this is a way that's straightforward in principle to see if you have a polar or a non-polar material, if your material has a centrosymmetry or not. Whereas X-rays do not show this. So in standard X-ray diffraction, the X-ray diffraction process adds center of symmetry back in. And so you cannot do an X-ray experiment, a conventional X-ray experiment, to see whether something is centrosymmetric or not. And so whereas doing nonlinear optics experiment gives you a straightforward way of looking for center of symmetry. So these are the actual data measured versus pressure. And this is from some years ago. And we've been trying to understand it ever since. So as he goes up in pressure, the signal goes down. And he looked real hard for signal at high pressure. So this is going up to 100 GPa. And maybe there's a little bump there. I'll talk more about this later. It certainly seems to get small in the middle. It certainly doesn't seem to be like what was predictive by Kornev and Balazs for this high pressure ferroelectricity. And so we were ready to say that there was no ultra high pressure ferroelectricity. I should mention, we also did the experiments at 10 Kelvin. I don't think I wrote that down here, but in order to make sure that it wasn't a matter of the difference in temperature from 0 to room temperature, the earlier work that we did with Mukhtar, we did have to go to low temperatures in order to see this monoclinic morphotropic phase boundary-like result. So I think these are the 10 Kelvin data over here, and you see that it drops essentially to 0 above 10 GPa. So it seems like there is no polar structure at high pressure. So that's shown again here for both single crystals and powders. The drop, maybe there's some signal up to 15 GPa or so, but pretty much by 10, it's mostly gone. So we've spent quite a bit of time trying to understand this, and these are our latest results. Finally, Yangzhen Lin has been working with me on this to try to wrap all of this up. And what we did was be very careful with our pseudopotential generation. And these are pseudopotential results shown here. But the other thing that we did that I'll be showing you is that we compared with all electron full potential LEPW in order to really make sure that there was no issue with pseudopotentials. It turns out that the pseudopotentials are really key to getting very accurate results here. And so in terms of the overall picture, we see the ferroelectric P4MM phase up to about 10 GPa. This is showing enthalpy versus pressure up to 150 GPa. And then there's a region where there's quite a few phases that are very close in energy, and there's maybe some monoclinic phases in here, but I'm not going to talk about those today. But it's mainly R3 bar C, so this is centrosymmetric above 10 GPa. And then I4 MCM, I'm going to say more about these, but this is another like strontium titanate, like rotated octahedra perovskite with no ferroelectricity. It's a centrosymmetric structure. And then if we had just quit at 80 GPa or something, then everything would have been clear, and we could have written our paper 15 years ago about absence of ferroelectricity in lead titanate, because this was completely consistent with the experiments, so that we had only the low pressure ferroelectricity and nothing at high pressure. But then we found, and this is what's really been soaking up all of my time, is at really high pressures, at above 90 GPa, this ferroelectric R3c phase comes back in with a vengeance. And so there really is a very, very robust prediction of ferroelectricity, ultra high pressure, even though it's non-ferroelectric for this whole range in here. And we were worried that this was some kind of numerical artifact or something for a long time, and have been working real hard to prove that that's not so. We also computed the polarization using the modern theory of polarization. You can see it dropping here in the tetragonal phase, and it's 0 all the way up to 85 or so GPa because these are centrosymmetric structures. And then at higher pressure, it comes back in, and I was thinking, well, maybe it's going to be a small polarization at ultra high pressure, but no, it actually gets to be even higher than the polarization at 0 pressure. So this is really fascinating to me. Oops. So showing a little bit more detail about those results and the testing that we did. On the left-hand side, I show the total energy versus volume. And there's a shift in the energy from the pseudopotential in the all-electron calculation, which is not really meaningful because the pseudopotential doesn't include the total energy of the pseudopotential, and we haven't probably put that in properly. We just shifted these arbitrarily to make them near each other. You can see that the LAPW results look similar to the all-electron results. The other thing you can see here, because like the pseudopotential results are all on this curve, if you only look at the total scale of the energy, you see all these ferroelectric phases. You wouldn't be able to see any difference in them whatsoever. So they fall just along what looks like a smooth equation of state. So the ferroelectric energy scale is order of magnitude smaller than the normal compression energy scale that one's thinking of in normal kind of phase transitions. Here, we show the points here are the pseudopotential quantum espresso points. And then the lines here are fits to the LAPW results. We don't have pressures computed directly with LAPW, so we fit a Vinet equation of state and extract the pressure from that. And you can see that it broadly, very closely mimics the quantum espresso results. It's also showing that this ferroelectric R3c phase is becoming stable at very high pressures. And here we show a direct comparison of the delta H going from the ferroelectric R3c phase to the non-ferroelectric IM4CM phase, which is the next higher structure. So you can see at above 90 GPa, this becomes negative, so the ferroelectric phase is stable, and you see that the LAPW and the pseudopotential calculations are really in quite good agreement. So the other thing I wanted to do then is, since we had measurements of second harmonic generation, I thought we should actually compute that, and that's possible to do now within the LAPW method. Oh, I should say we didn't do exactly LAPW. Advanced in the LAPW field as well, and I just didn't want to make this into a technical electronic structure talk. So what we did is called APW plus local orbitals, and it turns out that it allows you to get very accurate excited states as well as ground state frequencies. Of course, we still have the band gap problem that one has in density functional theory in general, and we've just used scissors operator, its fancy name for a constant shift, in order to correct for the band gap error at 0 pressure, and then just kept that constant. So that's a approximation in what we've done. But within that, we are able to calculate the second harmonic nonlinear optic coefficients directly in the ELK code. We're using the ELK, ELK LAPW code. And this paper by Sharma and Ambrosh Draxel lays out how this is done. It's actually quite involved, both conceptually and numerically. What one's trying to model is you have a photon that comes in and it excites an electron. That would be a normal optical process, a linear process. But in nonlinear optics, you have two photons that come in, and so they excite two different electrons, or the same electron twice by some energy. And then it drops down and releases a photon which has twice the frequency of the input photon. And so if you express that in terms of the polarization relative to the optical electric field, it's these coefficients chi ABC here, which couple two different electrical fields, or also shown here. Two different photons come in and one comes out at double the frequency. And we're using here a theory which is based on perturbation theory for non-degenerate states, and so we have to do some tricks to get rid of all of the degeneracies. So we have to shift the K-point grid so that we only deal with non-symmetric K-points, and we have to do a lot of things to make sure that we're getting robust and good results. So we've done these calculations, and they really look quite similar to the experiments. So the experiments, again, to refresh your memory, are shown here in this inset. Oops. And this is at 10 Kelvin by Mukhtar et al. And you see the SSG intensity as a function of pressure. Here it seems to be going to a somewhat higher pressure than at room temperature, and that's consistent with these monoclinic phases at low temperatures. But then at above 30 GPa, you see it's essentially zero. Well, is zero with measurable. So this is a third rank tensor, and so we calculated it. It depends on the symmetry of the system, which ones of these are non-zero. In the tetragonal case, there's 3 of them that are non-zero, and in the rhombohedral case, there's 4 of them that are non-zero. And then also calculated the average intensity for a powder, which is this d squared term here, which is the black. So what we're seeing is the calculated drop in intensity of but by the way, this is just a relative SSG intensity in the experiment, whereas we're calculating absolute intensity. But it's hard to measure absolute intensity, so we just compare the overall shape with the experiment. Anyway, at zero temperature, without including monoclinic phases, we're seeing that it drops until by over a factor of 2, and then which is pretty much consistent with what you see here, dropping down to about a factor of 2, and then dropping farther, well, in our case, to 0, because we didn't include the monoclinic phases here. When you actually look at the actual calculated spectrum, it depends on the wavelength, because what you're doing is exciting electrons of a given energy from below the band gap to above the band gap. And so this is the magnitude of the actual nonlinear optic coefficients, depending on the directions of the optical electric field. And we're measuring them at 1064 nanometers, so that's about 1.1 volts. So you can see the signal is actually fairly low in that region. I mean, if we could do it at much higher energies, but that wouldn't work because, oops, we wouldn't be able to get the energies out and measure them at, we have to deal with the situation that is technically possible. So most people do nonlinear optic measurements at these frequencies, but there is a predicted frequency dependence to the response. Okay, so now what I want to talk about in the last part is what's driving this high pressure for electricity. So that's really, I think this part we understand perfectly. So we understand up to 80 GPa. We understand how things go away in this complicated region here. And but now what's happening in the megabar pressure range? Because why in the world would something want to be ferroelectric at a megabar? So first, let me just show you some of the different things that we've looked at here. First, if you just look at the computed lattice parameters as a function of pressure, first of all, it's a little hard to track them when you just look at the lattice parameters themselves, as shown on the left diagram here. So we're going to tetragonal, and then as we go through different phases, of course, it looks like totally different lattice parameters. But we can reference these all to each other because we know what's actually happening. If we think back to the original structure of perovskite, these are all perovskites. And so we can look, for example, instead of looking at the tetragonal C and A here, we can compare the 101 in the tetragonal case with the not sure what it's not shown here, what that is. Anyway, we mimicked what's going on in the different structures as a function of pressure. And you can see then that they really behave very smoothly with pressure. There's no big jumps when it goes from ferroelectric to non-ferroelectric, or when it goes from non-ferroelectric to ferroelectric. Everything is completely smooth. And so that's certainly not going to be a way that one's going to detect the ferroelectric phase transition. And it also doesn't explain anything. What explains things a little better, of course, you need to know the positions of the atoms, which you can calculate very well in theory, is what's happening to the relative bond lengths as a function of pressure. Let me see, first we have titanium oxygen distances on the left and lead oxygen distances on the right. And the first thing I want to point out here, which really strikes out at you here, is that if you look at the ferroelectric phase at ultra-high pressure, both the short and the long lead oxygen distances are both much shorter than they are in the centrosymmetric structure. So we see that the lead and oxygen are trying to get closer together. Of course, with pressure, you're always driving things towards closer bond distances. So you see one reason that it wants to be ferroelectric is just letting all of the atoms get closer together, even the relative long distance. So it breaks the symmetry, it changes in such a way as to get denser, which is what pressure does to things, of course. If you look at the titanium oxygen distance, it's a little bit more subtle. What you find there is that in the rhombohedral case, there's 3 short distances and 3 long distances, whereas in the centrosymmetric structure, all 6 distances are the same. And so what happens here is 3 of the long ones tend to get a lot longer, and then the 3 short ones get a little bit shorter. And so the system is densifying, but it's allowing some of the titaniums to get farther from the oxygen. And so that also helps stabilize the high pressure structure. If you actually look at these structures and rotate them so that you can compare them, you can see what's happening here at least. It doesn't give you the reason why, but you can see it. So this is this I4MCM structure. So it's just like strontium titanate. You have these rotated, I hope it's like strontium titanate. Anyway, it's a rotated perovskite where you have one octahedron rotated to the left and the one below rotated to the right. And you see the titanium sits right in the center of the octahedron, and the lead over here sits right in the center of these octahedra surrounding it. So it's a very happy looking structure. When you go to the R3c structure, it's a little bit odd that this would be the high pressure structure. You see the titanium is no longer in the center of its octahedron, and you see it's moved off to the left. And this is the actual displacement, not exaggerated. So it's a pretty significant movement off center. And then the titanium, the lead, it's a little harder to see that it's actually moved, but it is off center here, surrounded by its oxygen, as I showed in the last figure. If you were to look at a predicted X-ray of the 2 structures, it should be pretty clear to tell them apart. So I was wondering if that was going to be the case or not. So if anybody wants to do megabar and above X-ray experiments, you can easily determine if it is the tetragonal structure or the rhombohedral structure. So maybe I can encourage someone to do that experiment. It's pretty hard, I think, to do the nonlinear optics above a megabar, but the X-ray experiment maybe is possible. And so you should be able to pick up if it says R3c structure. Of course, that wouldn't the X-ray alone wouldn't show you it was polar, but at least you would be able to tell that it was rhombohedral. Okay, so I've spent a lot of time trying to understand what drives this phase transition. And Kornev and Balazs, that was a key part of their long phase transitions paper. And really, it's quite an inspiring paper. It's worth reading about. I don't agree with everything in there, but I may agree with one of their bottom lines. But first, let me point out the things that are surprising and puzzling here. So if we look at the phase, the band structure, electronic band structure for the ferroelectric structure on the left, the R3c, and the non-ferroelectric I4 MCM on the right, except with the R3c labeling of the points here, or maybe it's vice versa. Anyway, they're labeled the same. So it's really hard to tell any difference here with the I. I mean, you can look at these a long time. I found some little differences, but generally speaking, you're not going to convince me that there's some big change in electronic bonding here between the one structure and the other structure. And also the color scale here shows how much titanium D there is in a given electronic state. And so the red ones are mainly titanium D, and there's a little bit of hybridization with the oxygens, which is the same as what I pointed out was important for driving ferroelectricity a long time ago. But it's not easy to see that it's so different in the ferroelectric phase and in the non-ferroelectric phase. In fact, they really look identical. So what you can do is you can add up the amount of each state up to the Fermi level. So this below zero here are the occupied states, and above zero are the conduction band states. So you see the titanium D states are conduction band states. So they're involved in the second harmonic generation signal, but they're not involved in the total energy directly. So if we add up the contribution for SP and D states for each of the atoms for the ferroelectric R3c structure and the non-ferroelectric I4 MCM structure, it's amazing how close they are. I really thought I must be doing something wrong. I must be looking at the same structure twice or something. So I checked this 10 times. It's really true. I mean, the lead S is identical in the ferroelectric and the non-ferroelectric. The titanium D is almost indistinguishable between the ferroelectric and the non-ferroelectric. And so you can't say it's due to some change in the PD bonding between the oxygen and the titanium or something like that. In fact, there's only one number that's different, and it boggles the mind. It's the oxygen 2s, which is not supposed to be involved in bonding at all. And I would think that this was amazing, except this is exactly what Kornev and Balazs said 15 years ago. So they said that I guess they went through the same exercise, and they decided that the only thing that they could really see that was different was the oxygen 2s. So you see that there's like so this is only counting up. I should clarify what these numbers are. This is how many electrons of a given character are in a sphere of a given radius around the nucleus. So it's hard to say what electron belongs to what. In quantum mechanics, the electrons just go everywhere. So you can't really say like this is an oxygen electron and this is a lead electron. But this is how many oxygens of angular momentum 0 are inside a sphere of like 1.55 Bohr around an oxygen. Okay, but the thing that's so clear is that the ferroelectric structure has much less of this oxygen 2s in the sphere than the non-ferroelectric. Now the thing that's interesting about this is there should be 2 electrons here. So you should have 2s electrons for each oxygen. So it means that the other half of an electron or 8/10 of an electron are sitting outside of that sphere. And they're not neglected. They're accounted for in the electronic structure, but they're just not counted here when I count how many electrons are in the sphere. And So that means that in the ferroelectric case, these s electrons have moved out to do other things. But it's hard to see. This is the actual electron density of states for the 2s states. And first of all, you see it's not a delta function. So it would be a delta function if they weren't involved in bonding at all. But on the other hand, you don't see any big change in the line width here or something that would imply some big change in the bonding. I'm going to continue with this in this next figure. This shows the whole band structure, but now highlighting the amount of oxygen S state in a given state. And it is interesting that there are some states over here in the conduction, in the bonding, oxygen 2b, 2p area that have oxygen 2s character, like over here, for example. On the other hand, this is mislabeled. I'm sorry about that. One of these is R3c. They do look identical, but they're not identical. One of these on the left here, this is R3c, not tetragonal. So this is ferroelectric and this is non-ferroelectric, and yet they look almost identical. So I don't know if this really supports the story that the oxygen 2s is the key or not. The other thing I tested just today, in fact, was looking at barium titanate at the same conditions, and now we see something. So if you look at barium titanate, we find that if you start with this tetragonal I4 MCM structure, it actually converges to be cubic perovskite at 150 GPa. And if you start with the R3c, it converges to R3m, but it's the same energy as the cubic case. So it really looks like barium titanate is not cubic at 150 GPa. This, by the way, is contrary to Kornev and Balash's results from some years ago. And you can compare this with the lead titanate, where you have this very strong ferroelectricity. So I'm coming to my bottom line here. I'm having a discussion, but that it's really, the lone pair is stupid, like I said, in 1992. So this shows lead titanate here. And you see the lead atoms, the leads are extremely polarized. So the leads are not spherical at all. And whereas if you look at barium titanate, the barium is really a spherical ion. And so it really is the polarization of lead, I think, that's giving rise to this, but it's not through a change in bonding, it's just through atomic polarization of the leads. So in the end, I think you have the Ewald part drives things off center, like we've always known. You have this polarizability of the O2s states, which I would say is not really fully understood still, but it's surprising. And then, but the key thing here is this lone pair polarizability, I think. So what do we learn from all of this? Well, actually, a number in this list is actually, I think, important for high pressure science in general, but let me just go through these in order. So maybe this is obvious, but when energy differences are small, you really need extreme care. So anytime you see somebody's prediction about something that involves some subtle small energy difference, you need to check and see what checks they did to check that it was really correct. And this can be especially sensitive in ferroelectrics because you have this delicate cancellation of long and short range forces, and it's just hard to numerically really get that right. And I would say that this has really taught me, over the decades that, first principles theory really does need to be tested by experiments. I mean, if we had never had Mukhtar's experiments, I guess we would have just believed the earlier theoretical work that these systems were ferroelectric under all conditions. And another one is that even the simplest ferroelectrics can be very complicated. A lot of ferroelectrics are a lot more complicated than lead titanate. So we can't, but like Slater said, well, there's some hope we can fully understand it. We think lead titanate's not ferroelectric from 20 to 85 GPa. And then the last two things are really the things that I think are the general lessons for everybody in this seminar. So first is that, and maybe we know this from many other works over the years, but compared with what we thought decades ago, it's surprising still to me, is that pressure doesn't necessarily inhibit phase transitions that bring atoms closer together. So you would think that that a phase transition, that repulsion, you know, like if everything was like a hard sphere, then things should want to stay apart, and not, you know, and they should want to try to find some way to stay apart within structures. But here we have systems that really distort in order to bring them closer together. And then the last thing, which is really a corollary of that, is that asymmetry can lower the energy and lower the volume, or give higher density, and lower the enthalpy in the free energy. So we shouldn't expect that ultra high pressure phases are all, you know, high symmetry, close packed structures. So, and at that, I'll open for discussion and questions.
Thank you, Ron, for a great talk. Glad to see this follow-up work. This is terrific. Okay, so I'm sure there are questions. Just unmute yourself or put them in the chat box.
May I ask, please, Cohen?
Ned.
Hi, guys.
Hi.
Ronald, it's a very good talk. I very much appreciate it. Thank you. I have two questions, actually. First, do you see something also on the electron density maps or LF maps when you're talking about the a lone pair or distribution of oxygen electrons somewhere?
Yes, I mean, this is actually computed. So this is a three-dimensional valence density isosurfaces. So so this is the titanium charge density. I mean, sorry, lead charge density that you're seeing here, that's distorted like this. So yes, in earlier papers we showed electron density maps of this in, you know, two-dimensional cuts as well. But yes, the answer is yes.
Sorry, I'm talking about. I assume that this is a how to say low pressure phase.
Yeah. So yeah, in the Kornev paper, I think they did some of that. Yes, they did show some of that at high pressure as well. We could, of course, compute anything you wanted for comparison with experiments, for example. So, but we do see the distortion, you know, polarization of the atoms at high pressure as well.
Thank you. And second question: when you're talking about the shift of titanium from the center of the octahedra in the high pressure phase, any numbers? How far?
Yeah. So this is, let me go back to the bond lengths here. So these are bond lengths in angstroms. Though it's spelled wrong, but anyway, sorry. Anyway, so it's a huge effect. So in the
huge effect.
Yeah. So it's like 0.1 angstrom. Yeah.
So okay, so it's in fact verifiable with the X-ray single crystal diffraction.
Yes, the thing that's not the thing that's not verifiable, as I understand it, in X-ray diffraction is whether you actually have a polar or a nonpolar structure. But once you take a model of a nonpolar structure, you could refine it, and you would get these positions, right?
We don't need. I'm sure that we don't need, if the quality of the data would be sufficient, to assume the structure. We should get it from the diffraction, but. Well, this is interesting task. Thank you.
Yeah. Okay, sure.
So on that point, though, would you need to do this experiment at very low temperature? Did you estimate the temperature effects?
I want to do that. So it's a very good question. Unfortunately, I'm not going to show it, but I'll tell you about it. So some years ago, Ganesh did some first principles molecular dynamics in this pressure range, and he found that it became centrosymmetric at about 70 Kelvin. But that was using different pseudopotentials that we think were less accurate, and they weren't giving as strong a ferroelectricity as we're seeing now. It depends on the pressure. So if you go back to this pressure difference, energy difference. So if you really were at 150 GPa, it's a very deep double well, and I think it's definitely going to be ferroelectric. If you were to do the experiment at 100 GPa, or even worse at 90 GPa, I think it becomes very iffy, and at room temperature, I'm sure you're probably not going to see it. So it really makes a difference which pressure you're dealing with here. So if you could do this, the single crystal diffraction 150 GPa, I'm willing to bet money that you would. I'll bet $1 to anyone that it's going to come out ferroelectric. Consistent with our structure.
Okay.
This is Roald here. Hi. Ron.
Hey.
It's very interesting to see these results. I wouldn't trust the projections at all. Look at your oxygens. The total number of electrons adds up to barely 5 electrons.
Oh, no. We're including all the electrons. I'm sorry.
Instead of 6 or 8. So I think it's just...
No. That's no approximation. I'm sorry. We have all electrons in our calculations. This is just trying to understand the result. When we do the calculation, we have all electrons everywhere and a full potential, and we've done it with 2 different underlying theories. We've done it with pseudopotential theory and all electron theory.
Ron, you're not listening. Look at the O results, 1.52. and then 1.20 for the 3 Ps. That adds up to 5 electrons.
Yeah. I'm sorry. I'm trying to clarify.
It should be 6 or 8, depending on whether you want it neutral or 2-.
Yeah.
So I wouldn't make too big a story of 1.52 because I don't trust that number.
No. Let me explain, please. We have all the electrons in the calculation. I'm just trying to understand what the result means. So these bands, for example, and the energies and everything are from all of the electrons. It's just in order to interpret the result, we divide space into these regions and look at how much is there. But that's just for understanding what changed. The thing that's interesting to me is not so much that 2 numbers changed, but all these other numbers stayed the same. But these are not an assumption. This is just like an analytic process after the calculation is done. So we have the right number of electrons in our calculation, and even not just now, but even 30 years ago, we had all of the electrons. All of the electrons are included in this charge density. You can't see where the sphere is here. There's a sphere boundary here. The representation of the electrons, outside the sphere and inside the sphere joins completely smoothly. In fact, that's an interesting story. I should tell this story because people probably don't realize this. There's a reason that this paper was sole authored. I was a postdoc at the time. So I worked for 2 years on this and was not able to find this double well. And I always got that the ferroelectricity was not happening. So people were writing papers based on my work, saying that you couldn't find ferroelectricity with density functional theory because it involved something that wasn't included in density functional theory. So this really is what got my career going. Remember, I started as a geologist. So I just didn't believe it. And so I was dealing with a 30,000 line code, and we had to run this on a Cray 2, somewhere else in the country. And you queued up jobs, and they would sit there for weeks before they would run and so forth. And I started going through all kinds of stuff in the code. And I found that the charge density, in particular what's called the pseudo charge density, was not smooth at the sphere boundary, where the muffin tin, it's called a muffin tin sphere, and it should be smooth. And so I couldn't figure out why it wasn't smooth. To make a long story short, it turned out there was a bug on the Cray where every 64th imaginary part of a complex number came out with the wrong sign. And if you did a centrosymmetric crystal, the wave functions are all real. And so all of the tests that had been done didn't find anything wrong because the wave functions were real. But if you had a complex wave function like you do in a polar material, then it made this error. And so once that was fixed, the ferroelectricity came out. So anyway, but things do have to be smooth at this sphere boundary, and we include all the electrons.
Yeah. Well, what one might have expected is some transitions under pressure. In general, electrons will get out of s orbitals and into d orbitals if they can. And so either the lead going from 6s to 5d or the titanium from 4s to 3d is what one would have expected. And the oxygen under pressure also would go up and maybe deplete, but you don't see the electron density going into the d orbitals, except on the titanium.
Right, let me show something because I actually was looking first for the effects of pressure on this structure. And I was very surprised, I didn't put it in the talk, but surprisingly, you don't see it. So comparing zero pressure and 150 GPa, there's very little change there's no like S to D or anything like this going on. Let me see if I can find it. I don't think anybody's seen me play around with this, right? I need to find it before I share it.
We're seeing it, Ron.
Oh, you are seeing it? You're seeing me page through my notes?
Yep.
Oh.
In your email.
Oh, in my email. How can you see all this? I thought I was just sharing. Let me share the right thing. What does my email say? Let's see. Well, you know what? I'm not going to find it on the fly like this. But anyway, it's you'll just have to trust me if you want to. But I looked for an effect on the occupancy of the states going from zero pressure to 150 GPa, and it's a very small change. It's not very significant. I would have liked to have found some big changes, but they just don't seem to be there. So when you compare the low pressure electronic structure and the high pressure electronic structure, it's really hard to make a case that any big change in behavior is happening from changes in the density of states or the occupancy of states. So it's a very subtle thing that's going on, and that's reflected in this very small energy scale. So if you look at a system that has real S to D transitions or something, then you see big changes in energy, and here it's just very subtle.
Okay, more questions? Well, I'm sure this is going to drive more experiments, Ron. So
I hope. We can also, do a lot more work with nonlinear optics. I mean, for instance, I mean, we're able to get the full tensor out, and so in principle you could do work, but it's very hard to interpret the experiments too, because you have these issues with phase matching and the refractive index, going in and going out and all this. So it's not going to be an easy set of studies. But if somebody's more, interested in doing further work on nonlinear optics, I think that, or even at zero pressure for that matter. I mean, I think technically we can do these calculations now, and should be fairly reliable. And so it kind of opens up a new area. You can actually, there's some papers, a few, very small number, but there's a few papers in the literature that actually look at, correlating nonlinear optic spectra and the band structure. So in principle, I mean, maybe it'd be useful for the, you know, for metals, or, well, I don't know how you do non-optics then. I guess you have to do it in reflection. So anyway, but in principle, it can be conducted even for metals and compared with the experiment. And they're very sensitive to electronic structures, so it should be a good sensitive test to what's going on in materials.
Okay, there are no more questions. Let's thank Ron once again. Great talk.
Thank you.
Good to see you
Great.
again.
Thank you.
Thank you very much. I really enjoyed it.
Thank you.
Okay, I'll say bye now. Bye-bye.